Hello everybody. So in the last video, we looked at how to find volumes using areas of cross sections. And a particular type of example we saw was how to find volumes when we rotate the region, which is bounded by a shape around one of the axes. So in this video, I want to slightly build on that. Instead of looking at just the area bounded by one shape, which we rotate, we'll look at rotating the area which is bounded by two curves. Or instead of areas which are rotated around an axis, we look at areas which are rotated around some other line. Okay, so let's get started. And each of them we can just handle with an example because everything is going to be similar after that. So let's suppose that we rotate the region bounded by the curves y equals x and y equals x squared about the x-axis. Our task is to find the volume of the resulting solid. So let's think about what that looks like on a picture. So before rotation, here is the line y equals x and the curve y equals x squared. And we're starting at x equals 0, we finish at x equals 1. So it's a very nice region in two dimensions. And then we're rotating around the x-axis. So as you can imagine, maybe if you rotate the region under y equals x around the x-axis, you would get a kind of cone with the inside filled. But then we're not rotating all of the region underneath y equals x, we're only rotating the region which is underneath y equals x and above y equals x squared. So rather than getting that whole circular cone under y equals x, we'll have to carve out the piece which is beneath y equals x squared, right? We do not include the piece which is below y equals x squared. So here is a picture of what it looks like after rotation. So we have this entire region where the dotted line represents the inside and the straight line represents the outside, and it's rotated around the x-axis. And in some places it's going to be pretty thick, say in the middle it's quite thick, whereas at the end point it's quite thin. So it's kind of like a circular cone with a piece carved out of it, and how much is carved out depends on where we are, right, according to y equals x squared. So now how do we find the volume? Well, let's go back to basics. Remember we said that to find the volume of a region in 3 dimensions, we should pick a point x on the x-axis, look at the cross-section, find the area of that cross-section, and then integrate it. So if we look at this cross-section, it's going to be, the large one will give us a circle, right? The y equals x rotated around will give us a circle. But also rotating y equals x squared gives us another circle. So we're rotating the difference between two circles, right? If we look at the cross section, we have this kind of ring, and the middle is carved out of it because that's the piece underneath y equals x squared. So if we want to find the area of this kind of ring, we should do the area of the large circle minus the area of the small circle. So that means we want to find the radius of each of those. So here is this kind of annular ring. The inside and the outside have different radii. So how do we find the radii? Well, the outer radius is going to come from y equals x because that's the furthest from the axis of rotation, right? So this is going to be x, and the inner radius is x squared because that's the inner circle. So here we see the inner circle comes from the curve y equals x squared. The radius of the inner circle is the y value there, which was x squared. The outer circle comes from the curve y equals x. So the radius of the circle there is the value of y in this case, which is x. Okay. So now we know what the inner and outer radius are. We can find the area. We just do the area of the large circle minus the area of the small circle. So the large circle has radius x, so we're going to get pi x squared. The inner circle has radius x squared, so we're going to do pi times x squared squared, right? Always pi times the radius squared. So we get pi x to the 4. Okay, so this is our area of our cross section. And then once we find the area of the cross section, it's the same story as before. We just have to integrate the area of the cross section. So in this case, we're integrating from x equals 0 to x equals 1. That's when the region starts and ends. So we integrate from 0 to 1, our a of x, our cross section. We pull out the pi. We have to integrate x squared minus x to the 4. Antiderivative will be x cubed over 3 minus x to the 5 over 5. We plug in 0 and plug in 1, take the difference, find the common denominator. The answer in the end will be 2 pi over 15. So here we saw that if we want to rotate a region which is bounded by two curves around an axis, then the cross sections are not going to be circles anymore, but are going to be washers because the region was basically a difference of regions of curves. So the cross sections are going to be a difference of circles. It's going to be this kind of washer shape or ring shape. To find the area, you're going to want to figure out which are the outer radius and which is the inner radius. Those are going to come from the y values of the curves in this case. But if you're rotating around the y-axis, instead it will be the x values. So you're going to have to pick the correct one depending on the curve. And then to find the area of this cross section, you're going to do the radius of the large circle minus the radius of the small circle. Okay, so the next thing to think about is what if instead we're rotating around an axis which is different to the x or y-axis. So in all the previous examples, we rotated around the x-axis or around the y-axis. So let's say we're rotating around the line y equals 2. Okay, so here is the same shape, right? We have y equals x squared, we have y equals x from 0 to 1. They form this region, and now, like before, we rotated around the x-axis. Now we're rotating around the y-axis. And the story is the same. The only things that change are the radii. So we need to find again the inner and outer radii of the disk. So if we imagine this shape is rotated around the axis, around this line y equals 2, so y equals 2 is up here, then we're going to get some kind of region, and it's going to be a large region with a smaller region subtracted from the inside. And the smaller, the inner radius is going to be the part which is closer to the line y equals 2, right? That's going to be, because we're not including all this piece which is bounded by the inner radius. So the inner radius is going to be the curve which is closer, which in this case is y equals x. So it's going to be the distance from y equals 2 to the line y equals x. Okay, that's 2 minus x. And then for the outer radius is going to be generated by whichever curve is further away. So in this case, the curve that's further away from the line y equals 2 is y equals x squared. So the outer radius is going to be the distance between the axis and our further curve. In this case, it's going to be 2 minus x squared. So you can imagine that when we rotate this region around the line y equals 2, we get some kind of solid. And if at x, we make the cross section through x and perpendicular to the x-axis, we get an annular ring. The inner radius is 2 minus x. The outer radius is 2 minus x squared. Okay, so now that we figured out the inner and outer radius of the washer, we just have to do, a of x is going to be the area of the cross section. So it's going to be the area of the washer. So we have to do pi times the outer radius squared minus pi times the inner radius squared. So the outer radius was 2 minus x squared, right? It was the distance from y equals 2 to the outer shape, which was y equals x squared. The inner radius was 2 minus x. So we have to do pi times one radius squared minus pi times the other radius squared. This is going to give us our area a of x. Okay, now all we have to do as before is to integrate a of x to get the volume. So in this case, it's going to be pi. We pull out the pi. We have to integrate from x equals 0 to x equals 1, 2 minus x squared minus 2 minus x squared. And it will be a mess, but if you can multiply out, you get a polynomial, you use the power rule, and collect everything, you'll get 8 pi over 15 in the end. Okay, so in this video, we talked about two extra types of examples. Those are when we rotate the region which is bounded by two curves around an axis. In that case, we're going to get a washer, which is a big circle minus a small circle. To find the area of that, we have to find the inner and outer radius, going back to the original picture. And then we have to do the area of the large circle minus the area of the small circle. That gives us a of x, and we integrate it. And then if we're rotating around an axis which is around a line which is different to an axis, the strategy is pretty much the same. The only thing that changes are the inner and outer radius. So the inner radius, we're looking at the distance from the axis of rotation to the inner part of the shape, or to the closest part of the shape. And the outer radius, we're looking at the distance from the axis of rotation to the furthest part of the shape. Okay, that's it for today. Thanks everyone. See you next time.